Hi, this is Scott Wilkinson, host of Home Theater Geeks. In episode 173, I chat with Paul Barton of PSB Speakers about his research into designing better headphones. Coming up next.
Netcasts you love.
From people you trust.
This is Twit.
Bandwidth for Home Theater Geeks is provided by CacheFly at CACHEFLY.com.
This is Home Theater Geeks with Scott Wilkinson, recorded September 9th, 2013. Episode 173, Designing Better Headphones. This episode of Home Theater Geeks is brought to you by ProXPN. ProXPN is a virtual private network that allows you to use the internet the way it should be, anonymous and unfiltered. For 20% off your new account, go to proxpn.com/twit and use the promo code HTG. Hey there, Scott Wilkinson here, the Home Theater Geek and Director of Content at avsforum.com. This week's guest geek is Paul Barton, the founder and chief designer at PSB Speakers. Hey, Paul, welcome back to the show.
Good to be here.
Always great to have you on. Lots of interesting things to talk about today. Those of you who are tuned into the live stream at live.twit.tv or logged into the chat room at irc.twit.tv can post questions for Paul as we go, and I will pass along as many as I can. Now, Paul, you've been designing speakers for many years. How many years has that been now?
Well, this will be 41 years.
41 years of designing speakers. Recently, you started making headphones, including the ones you and I are both wearing right now. I'm wearing the original M4U2s, which are noise cancelers, and you're wearing the M4U1s, which are passive headphones that one might use with a portable player or whatever. Tell us about how your approach to headphones has evolved over the last year or so since we last talked about it.
Well, I think I said back then that the listening habits of people these days has been quite a bit changed, and that people take their music with them, with their smartphones, etc. So being in the sound reproduction business, and we are specialized in loudspeakers, turning electrical energy into acoustical energy. Why not try and appeal to the younger crowd, and certainly our diehard audiophiles of late and of the past also listen to their music more portably. So I was able to tap into some research that was done in parallel with the research that we're well known for or being a part of. And that's the research that took place in the mid-70s right through to the late 80s on the correlation of subjective versus objective measurements of loudspeakers.
I must interrupt you just for a moment there and say that every once in a while I run a poll on avsforum.com, and this week's poll is exactly that, asking people whether they believe that whether audio measurements, objective measurements, correlate with the subjective experience or the subjective sound quality of audio products in general. You're talking about speakers in particular, and that's one example. But so anybody who has an opinion about that, go over to avsforum.com and vote in that poll. But I just wanted to bring that up because that's what you're about to talk about.
Right. And it's well documented, the subjective versus subjective measurements of loudspeakers, which were centered on the research that Floyd Toole headed up in the mid-70s to late 80s. And really that came to a basic three conclusions. First conclusion is that most of the people, most of the time, agree on the relative qualities of a group of loudspeakers. What that means is that there is no regional, cultural, ethnic type of sound. It's something that we process and compare and meter against what natural sounds are like. And we adapt to that. We recognize it just like we do facial recognition. We have the ability to listen to things and identify them, and that's all based on our ability to perceive details in sounds that allow us to see what that fingerprint is, or what that character is, or what that instrument is. So we all have that ability, and we all develop that ability with natural sounds, human voices, cars driving, wind blowing, leaves flurrying in the trees, so that we aren't necessarily built in different ways in different cultures and different countries. The second thing that we've learned is that most of musical experience and musical taste are no prerequisites for being a good judge of sound. And all of this came out of the kinds of subjective evaluations we did, asking people what they thought of sounds, how they compared sounds. It's a very laborious, time-consuming, and difficult task. And sorry about that. A very difficult task. And this is why a lot of this research has never been done in the past to that degree. The third thing that we've learned is that a properly interpreted set of objective measurements, that's all the measurements you would do on the loudspeaker, and we do these kinds of measurements in a dead room or an anechoic chamber, which really allow us to look at just the device, the speaker itself, as a source, and don't worry about the environment that it's in, because the environment that it will be put in can be quite profound in how it influences the sound. And we'll talk about that a little bit later. So these are the three fundamental bases on which we know that if you do it right, you hit the right target function, people definitely will prefer it. And it isn't populated by people in different regions for different kinds of sounds. We all tend to agree. So that leads me to the next step, and that was, well, if we're going to listen to headphones, and we're going to listen to those headphones on music that is normally recorded to be played back on loudspeakers, you have the room that you play the speakers in actually performs or behaves like a filter, so that through the sound you hear coming from the source through the loudspeakers also has to come through the room, the environment that you're in. And typically, because most direct radiating loudspeakers radiate at low frequencies in 360 degrees, and as the frequencies get higher, the dispersion becomes narrower and narrower. What that means is that if you looked at the total energy that the speaker puts out, it will be a combination of the direct sound from the loudspeaker that arrives at you, and in addition to some reflections that occur in the room, and it'll depend on how reflective the room is. At very low frequencies where the room is not very reflective, you'll get additions and subtractions. But the overall impression you will get is an increase in the low frequencies, particularly below about 200 cycles.
Now, is that because of what we call room modes?
Well, room modes, and also the fact that at low frequencies, the speaker is omnidirectional, and at high frequencies, it's directional. So that there's more energy in the room at low frequencies than there is at high frequencies. And that is, if you wanted to profile what that relationship was between low frequencies and high frequency energy, you would do what we call sound power. And that is the total energy that's radiated around the loudspeaker at all frequencies. And it's not the same for a direct radiating loudspeaker. So if a direct radiating loudspeaker fulfills the illusion of good sound reproduction when it's put in a room, in order for you to appreciate that same sonic signature, you must also add the room gain to the headphone. And this is something that we call room gain, something we call room feel. One word, ROM, capital F-E-L-L. And
F-E-L-L or F-E-E-L?
Sorry, F-E-E-L. Sorry. I don't
now,
have
this is a term that you're actually copywriting to indicate something very specific.
Yeah, it's to point to this approach to a headphone.
Right.
And I'll just go back a little bit to how I kind of segued into this approach. As you know, and as I've just explained, all of this research that went on at NRC, in parallel with this research, there was a gentleman or a researcher at NRC. His name was Dr. Edgar Shaw.
Before you go on, I want to just make sure everybody understands that NRC is the National Research Council of Canada, which is where you are and where this research was done. And they have all sorts of very sophisticated testing facilities with anechoic chambers and all sorts of stuff, which is why you can do this kind of research there.
Well, actually, I'll just mention that NRC is a government-funded sort of think tank. It employs about 1,000 PhDs in all of the sciences. And acoustics or physics or microstructural sciences, as they refer to it, is a subset division of this scientific think tank. And I was fortunate enough in the mid-'70s to be introduced to this facility and haven't looked back since.
You've been using it ever since, haven't you?
That's right. I've been going there since 1974. And I'm usually in the chamber or in the facility, I would say on average about a week every 6 weeks. So that sort of gives you the amount of time that's spent in this type of environment.
Right. I wanted to ask you, before you go on, I wanted to ask you a question. You're talking about room feel and how the room plays a profound effect on the sound that you hear from loudspeakers. And yet one of your three tenets that you talked about earlier was to do the measurements in an anechoic chamber where you're only measuring what the speaker is producing, not what's happening in the room. How do you correlate these two? Or how do you take the anechoic information and predict in some way, or can you even how it's going to be changed in a room, because rooms are so different. One
they
room
are,
to
another. But the general trend and what we're trying to achieve with the headphone. I mean, I'm not suggesting that if you take a PSB and put it in any room, it's going to be perfect. But
right.
What I am saying is that if you know that the room has this phenomena and you optimize it so that you don't allow these standing waves, as you referred to them, to clump up in the same location at a lot of different frequencies at the same location, it will have a very negative effect if you allow this to happen. A good room has standing waves, but a good room with the right proportions can minimize the standing wave or can actually spread out the standing wave distribution in the room so that there are no severe problems in any place where the problem might be clumped together, so that when you're sitting somewhere you have no bass or you have too much boom. Or these are the things that rooms can do that are sometimes hard to control if the proportions or the treatment in the room isn't ideal.
Right.
So what I'm saying is that if you take a room and you optimize it and you look at distributing the standing waves throughout the room evenly, the amount of, or the transfer function that you will get that people like the sound of when listening to normal recordings will be one that has a certain tailored shape in the frequency response after you take a flat loudspeaker and put it into a room. But the flat loudspeaker isn't just flat on axis. It also has to be well-controlled off axis, because a lot of what you hear in the room, as I suggested earlier, is the combination of direct sound and reverberant or reflected sound. You have direct sound, you have early reflections, and then you have all the tangential reflections which accumulate and become what we call reverb or echo reverb.
Right.
So
and by the way, what is that? You talked about the profile, the frequency response profile in a room, the target
function.
Target function. What does that look like roughly?
Well, that's what we're working on right now. And the, the M4U2 is our first sort of segue into this approach. Same with the M4U1, which I'm wearing. What I did was I took what I thought was the typical room gain that occurs, and also at high frequencies, there is a slight roll off of energy, because when you move away from the loudspeaker, the energy the tweeter is producing eventually gets weaker with respect to your source, because as you move further and further away, you hear more of the reflections. But because the tweeter isn't really producing a lot of off-axis dispersion to the same degree that a point source at low frequencies with much longer wavelengths has, then you will see that in a room, a flat loudspeaker up to 20 kilohertz will actually have some high frequency attenuation when you put that speaker in a room and listen to it in a normal position. Believe me, that's what happens. So with a headphone, you also have to put that slight roll off at the high end. And the secret sauce that you're asking for, which is the target function, is something that I believe I have a secret sauce target function, but I believe that there's even better ways to improve it. I'll give you an example. When you've got your headphones on, excuse me, you're not really allowing your ears to differentiate sounds that are coming from above, from behind, or from in front of you, because the pinna now is basically not being used in the same way that it is when there's no headphones on your head. And
even with over-the-ear headphones such as these?
Yeah, the pinna is functioning, but not in the way in which it was designed, because you're really changing the environment around the pinna.
Right.
So I'll give you an example of this, how specific the pinna is with regard to where sounds are coming from.
By the way, the pinna is the outer flap of the ear, just to make sure everyone understands.
That's right. It's the part we see. It's the part we see on the side of our head. And this is sort of a bit of homework for your readers. What I'm asking you, and you can try and do this as well, just to see this phenomena or this effect. If you place a pair of loudspeakers, just like I have a pair of the PSB PS1 powered computer speakers in front of me. And if I were to play music on those two speakers, and they're fairly close in near field, so I'm hearing the speakers mostly, and I'm not hearing any reflections that are in the room. Mm-hmm. And if you sit in front of them and you listen to some music, and then you repeat that music, or as you're listening, you put your head so that the top of your head is pointing at the loudspeakers.
So that you're looking down at the floor, in other words.
That's right. And then again, listen to the timbre of the music when the music is hitting the top of your head, and you will hear a distinct increase in the frequency response from about 4K to about 7 or 8K. And it varies with individuals because of the pinna size, but it's definitely there. And the reason it's there is that when a sound is above us, the timbre of the sound above us is different than the sound in front of us. So these are the kinds of spatial coordinates that the frequency response differences at different angles around the ear are able to distinguish. The brain is already programmed to figure that all out, and that's how we can tell localization. But when headphones are on, what should the frequency response be? Because the sound isn't coming from above. And if we were to listen to a loudspeaker whose boost at 5 to 7 or 4 to 8K was the boost that we hear when we put our head forward, we would say that speaker is too bright. But why is it not too bright when we put our head straight forward? This is all very complex processing that's going on inside our head. And we're trying to do research to try and better understand and then better implement whatever this target function ideally needs to be. But I think we're on the right track. And there is evidence of this happening. Go ahead.
I'm sorry. I was gonna ask. You wouldn't want the target function to sound like you had your head looking down at the floor towards the speakers, right? You would want to make it as if you were sitting there in a normal seated or standing position with the speakers coming at you this way, right?
That's right. So how do I attach a target function to the listening experience when we know that the ear hears and delineates things from different directions in different ways? So,
right. In fact, SoCal Ray Jr. in the chat room brings up a point about this, which is that it has this whole thing we're talking about has a lot to do with human hearing perception and how well humans hear low frequencies versus high frequencies. For example, it takes a lot more level to perceive a very low frequency than it does particularly a middle high range.
yeah, and I think that evolved over time because our ear has, if you measure the frequency response of a flat sound entering or at the entrance to the ear, and you measure it at the eardrum, there is a distinct change in frequency response because of the characteristics of the ear canal. And this is something that is a real challenge because how do you simulate that environment that allows you to see what's happening at the eardrum when a natural sound or a acoustical sound is present at the entrance to the ear, and where it comes from and what the frequency response components are relative to each other. And our ears have developed around the ability to survive, and survival is very dependent on communication and being able to localize sounds so that we can determine whether we're safe or not. And
right. Tyle Hertzens uses the example of we need to be able to tell from which direction a twig snap occurred because that may be a saber-toothed tiger coming after us. And exactly. I pointed out that another issue that's very important is the fact that in human communication, the consonants are typically occur in the 3 to 5K range, which could explain why the ear is most sensitive to that sort of middle high range of frequencies.
And do you know why the ear is most sensitive in those frequencies?
Well, we were discussing on the last episode, Tyle and I were wondering what was the cause and what was the effect. Language occurs in that area, so the ear became more sensitive, or language developed to be in that area, the consonants to be in that area, because the ear was already most sensitive. What's your take on that?
Well, all I can tell you is that the ear evolved so that it had a very efficient resonance in those frequency ranges, which means
resonance within the ear canal.
That's right.
Ah.
That's roughly where the ear canal resonance occurs, so that there is an actual about a 15 dB boost at 3 kilohertz. If you put a sound in the ear at 1,000 hertz, and then you put a same sound and measure at the eardrum at 3 kilohertz, there'd be as much as 15 dB boost.
Wow!
And that allows us to hear the twig snap even at very low levels because our sensitivity is so high. And what it means is that sounds that are on either side of those frequencies aren't as sensitive, so that the one frequency really stands out amongst other sounds that are happening around it. And and so, yeah, that's basically what's happening.
Gotcha. SoCal Ray Jr. is also mentioning something called the Harman Curve, which I'm sure relates to Floyd Toole's research and that of Sean Olive as well. He says that the Harman Curve has 5 dB high on the bottom end and 5 dB down on the top end.
At the extremes, that's right. And actually, that's the target function that emulates the kind of transfer function they achieve when they set up an ideal sound in their listening room. And their listening room is optimized just like a good listening room I was talking about earlier. And they basically tried to map the target function to match that listening room. And when they do that, Sean has written, I think now 3 papers on the subject that were all presented at the Audio Engineering Society convention since last. I think he did one in October, one in May, and another one recently in August in Helsinki, Finland. And the conclusions there is that we're on the right track. and it's not surprising to me that we've both we're on the same path, simply because we come from the same pedigree of knowledge, I guess, and that's the National Research Council. You know, Sean worked under Floyd Toole when Floyd worked at NRC, and Sean joined Floyd to work further and do research for Harman, which he currently is doing now. And he and I have talked about this, and I think we're hot on the trail of, I would say, raising the bar on what a headphone should be. I want to emphasize, though, that this doesn't negate headphones in the past, because a lot of the headphone research done in the past was a lot based on hearing aids research and couplers that emulate the transfer function at the eardrum, most of which were optimized up to about 4 kilohertz. But beyond that, there wasn't really a lot of interest or data accumulated, because it was really designed, this research in the past was designed mostly for hearing aid research rather than high fidelity research. They can be quite different.
Yes, and as a matter of fact, if somebody goes to an audiologist to get their hearing tested to see what their particular hearing curve is, most audiologists don't have equipment that goes up to 20K. It only goes up to maybe 8K,
right?
Because all they're concerned about is speech.
Yeah, intelligibility and just to be able to function. That's the requirement for an audiologist. It's not an audiologist doesn't require a person to be an audiophile.
Right. So if you're an audiophile and you're looking for an audiologist to get that hearing test, be sure that you ask if they have the equipment that'll go up to 20K. Not many people do, but a few do. So you'd be lucky if you found one, and definitely go take advantage of that particular audiologist.
And I would challenge anyone who thinks that they can measure accurately above about 4 kilohertz, because the standard today doesn't really give you much repeatable, or I'm not confident in the information that we get from standard measurements using standard couplers. So maybe we can get into a little bit about some of the research that we are doing. And you had mentioned that you had talked to Tile a couple of weeks ago about the same subject. And
yeah, we mentioned it. We brought it up just briefly, that, you know, he's very good with headphone measurements. He has a very expensive dummy head and an isolation chamber, essentially an anechoic, tiny little anechoic chamber for measuring headphones. And he's very big into headphone measurements. And so we just mentioned it because I knew you were coming on in 2 weeks to talk about this more in depth. Now, so please let us know what it is you're doing in your research. And I think you have some graphics to show us here along the way as well.
Well, first of all, maybe you could put up KEMAR, which is the dummy head torso. I sent a picture of it, which is simply a very well-known industry standard for doing headphone or any kind of ear pinna. You can change the pinna on KEMAR. And this particular pinna was one that was used by Dr. Edgar Shaw at the time I first approached the National Research Council back in 1974. Edgar was the section head for the acoustics, and Floyd was one of the researchers that worked under Edgar, who was the section head. And Edgar was actually the person that was doing research on the external ear and the pinna. And he basically mapped what I just described earlier by saying, if you move your head forward and listen to music, it sounds much more boost in the high frequencies as opposed to listening directly in front of you. these are the things that he was profiling mostly for the hearing aid medical industry, but all of this still can apply to headphones. The problem that I've discovered in developing headphones with this original apparatus is that there is room for improvement on developing a measurement system or a coupler inside the mannequin head that is better representative of the human hearing mechanism, right up to as high a frequency as possible. And so this is what we're in pursuit of. Edgar did the basic work on it, and as you just showed a minute ago, that was the test apparatus KEMAR. What you see here is the KEMAR is in the anechoic chamber, and what I'm doing is I'm measuring the isolation of a sound outside KEMAR when I put the earbuds into KEMAR's ear to see what kind of sound isolation the little ear gels create.
Okay, so this dummy head KEMAR has earbuds in its ears, in those very carefully designed outer ear parts of his head.
Yeah, those are actually replicas of a real human ear.
Oh, really? Oh, I thought it was some sort of average.
Well, it is, but it's one that was chosen that is an average.
Oh,
but
some individual who happens to be pretty close to average.
That's right.
Oh,
that's
okay.
Right. And the microphone is to set what sound pressure level is at KEMAR, and then there is a speaker in the foreground that you see. You can see the back of the speaker, which is generating the sound source that I can actually now measure with the microphones inside the ear canals of KEMAR what the outside sound isolation is, and I can also measure the headphones themselves in this apparatus. Mm-hmm. Right now, KEMAR has a coupler in it, which is called the Wisłowski coupler, and it was well known in the mid '70s as the standard for an ear coupler that represented the impedance of an ear canal of a human being up to about 4 kilohertz. But beyond 4 kilohertz, this ear canal does not represent a human ear canal. So I think I also have a picture of a ear and cheek apparatus, which I believe is the same apparatus that a few people use in the industry. I know that Brent Butterworth of Sound and Vision magazine uses this device. I think Sean Olive uses it as well. It's a simulator with an ear canal, and you can put a pinna on, and you can see the little clamp on top allows you to clamp either the earbud or the over the ear or on ear headphone on top of it. And then coming out the bottom is the signal measuring what's happening at the end of the ear canal coupler.
Now, is this the same ear as on KEMAR?
This is the same ear that you see on KEMAR. That's right.
Okay.
And there is a few different standard KEMAR ears. One is the male left and right, and then there's also a female standard left and right, which is a smaller pinna. And what we have here is a standard. It has an IEC coupler, which is the standard coupler. Again, it's not exactly the same as the Wisłowski coupler, but it does give you reasonable, repeatable, and accurate measurements, but not really discernible accurate measurements above about 4 kilohertz. What I would like to see happen, and it just so happens that 2 of the researchers that were students or postgraduate students of Dr. Edgar Shaw at the National Research Council, one's name is Gilles Degg, and the other is Mike Stinson. And both of them worked with Edgar Shaw to further develop the ear measurement system and simulators for measuring devices. In their case, again, was with hearing aids. But we've collaborated together recently, and they are now working on a project that we are in pursuit of making a model of a very accurate ear canal, which will be accurate, we believe, up to about 14 to 15 kilohertz. And
extending the range beyond the hearing aid range, or 4K, as you said, in past models.
That's right. And again, better enhancing what the real target function needs to be in the ear, and understanding more about the subtleties of the changes within a human ear. One might say, well, if you make an ear canal that's equivalent to one human being, will it apply to all other human beings? I don't think the frequency response detail and the peak at 2K or 3K or 4K will be the same for all people, but it's all relative to the particular individual. And so we want to make a headphone that really represents the acoustical event as it enters the ear, and then the person's ear canal can kind of take whatever acoustic information appears at the entrance of the ear canal and do its magic for the particular individual based on the length, the diameter, and the shape of the particular ear canal that the individual has. But we have to start somewhere, and our first attempt, believe it or not, is with the ear canal of a woman. It's a female ear, and we're also using a female pinna. It just happens to be a good starting point for us. And like I said, it's only a starting point. I think I put a few graphics together to show you a replica of the ear canal. And let me just describe what this is. The green section you see is basically the physical coupling device that allows me to put it into that plate that you saw, the ear and cheek plate. And then the blue section you see is actually a 3D scan of an ear canal of a female left ear from a cadaver, from a human cadaver, so that it is exactly the same shape and diameter, and everything is identical. And then at the end of it, you'll see this, what is it, yellow colored,
brownish colored, yeah,
brownish yellow colored device. And what that
like
is,
a cylinder.
Yes, it's a brass cylinder, which, and if you show the other image, I think there's, yeah, you can see the purple in the bottom is the opening entrance to the ear canal, and that would couple with the pinna. And in fact, the opening to the ear canal in this case, and in most cases, is not round, it's somewhat oval. And then the blue snakes through the green section, and then you see this, like I said, this brown thing on the end. And what that is a device that has been machined to replicate the acoustic impedance of the diaphragm of the eardrum. And how that's achieved is that piece of brass, if you see where it's attached to the blue, if you took that off, you would see a round surface. That round surface, which is about less than a 1/4 inch in diameter, round surface, has about 500 holes in it. And the holes are different lengths. And what that does is that produces a little, what's the word I'm looking for? A little kind of spring or pin cushion, which is all these little channels of air which are drilled into this plate. And that basically simulates the
acoustic impedance of the eardrum.
Yeah, the acoustic damping of that diaphragm of skin in front, which we call the eardrum, which is attached to the little bones inside that excite the hairs in the cochlea.
Right.
So,
now, the eardrum itself is not perforated. It better not be anyway.
No, it's not perforated, but this device is acoustically similar, or its impedance acoustically is the same as if I put an eardrum at the end of that blue section.
Right.
If I were to, and then what we do is we take where the junction of the brown section and the blue section occurs. There is a probe microphone. There's a tiny little hole drilled in the side, and the end of the microphone is just like a pin. And it goes inside and is just at the opening or at the entrance or at the surface of where that eardrum would be. And that's where we make the measurement, so that the actual measuring device does not get in the way of the actual device it's measuring.
I've always wondered about that, actually, that, when you're measuring something in the eardrum, I think Tile puts a microphone into the simulated ear canal and so on, but I've always wondered how that might affect the measurement itself because of the presence of this thing that wouldn't otherwise be there.
That's right, and that is a challenge. A probe microphone, getting it in there. There are lots of people who have done this sort of thing before, but I believe that if we take this approach, we will have a measurement system which is better. When we have a better measurement system, we can do more listening to headphones, try and tailor it to what we think this room transfer function or this secret sauce needs to be, which I think we're pretty close already. I mean, the results that we've gotten feedback on our headphones in the critical review community has been very positive on this approach. People don't know why they sound as good as they do, but this is why. This is the approach. And I think from what I can tell, Harman also understand that this is a good approach to making better sounding headphones.
Before we continue, I'd like to take a moment here, if you'll excuse me. We got more to talk about. Don't worry about that. But I would like to take a moment to thank our sponsor for this episode, which is ProXPN. Now, ProXPN is a global VPN, virtual private network, that works with just about any internet connection. And it creates a secure encrypted tunnel through which your data flows, safe from prying eyes, which, as we know today, as Leo has talked about lately, very, very important to keep your system secure if you want to be protected from all of the spying that's going on. And it includes, your web browser, your email, file sharing, instant messaging programs, all that stuff. Keeps everything you do online hidden and disguises even your physical location, gives you unfettered access to any website or online service, no matter where you live or travel to. Now, ProXPN offers this privacy with a 512-bit encryption tunnel, which, as we know, there's no encryption that can't be broken, but that one's going to be really, really hard. It works via OpenVPN or PPTP. You can choose whichever one you want. It protects you against your ISP's 6 strikes rule and keeps your personal internet usage private at work. So that's really important for those of you who are surfing the web on company time. It bypasses internet filtering and blocked websites, also geographical restrictions for internet content and online video with worldwide servers in the US, UK, Asia, and more. ProXPN makes your internet connection truly region-free. There's software for Windows and Mac that offers advanced controls, allowing you to select the programs and ports you want to anonymously route through ProXPN's servers. It's also available on iOS and Android devices, letting you use your data plan and public corporate Wi-Fi with complete and total privacy on the go. And in fact, there's a new ProXPN app for Android in the Google Play Store that supports OpenVPN. Steve Gibson, Twit's own security expert, gave it a great review on Security Now. So go to proxpn.com/twit for more information and to sign up. ProXPN premium accounts are normally $9.95 a month or $74.95 for the entire year, but we've got a special offer for Twit listeners. In fact, for HTG, Home Theater Geeks listeners, use the code HTG and receive 20% off for the lifetime of your account. That's less than $5 a month on the yearly plan. And if you're not satisfied, you can cancel within 7 days for a full refund. So go to proxpn.com/twit and use the promo code HTG. And we thank ProXPN so much for their support of Home Theater Geeks and the entire Twit network. So, Paul, you had just told us a little bit about how you're doing these measurements, how you're incorporating or researching how to incorporate room gain or the room transfer function into headphone design, much as Harman is also doing. Do you know of anybody else doing similar research?
Well, I attended one of the papers in Rome that Sean had done, and it's pretty clear that it was well attended, and some of the players in our industry, in the headphone industry, were present, it's a bit too soon to see whether these people are willing to look at this research and adapt it. If you listen to headphones even prior to now, first of all, it's quite a range of sounds coming from headphones. And it sort of reminds me of the day when I first approached NRC or was introduced to Floyd Toole at NRC. When we did subjective evaluations in the early days of different brands of loudspeakers, they were dramatically different from one another. But nowadays and I think part and parcel of the research and the understanding of how speakers are supposed to reproduce sound and be natural, most speakers that are good today, the better speakers out there, tend to sound more and more similar. And that's a good thing. Headphones aren't there yet. And some headphones have this room gain boost, but I think it's somewhat arbitrary. And I'll tell you what I mean by that. When someone listens to sort of the engineers give the marketing department a pair of headphones and say, okay, what do you think of these? These are the flattest headphones we've ever measured. They're perfect. So they put them on and they listen and they go, not enough bass. And it's because this room gain needs to be included. And so what the engineering department would do at that point would be, okay, well, we'll just give them more bass. We'll take our flat headphone and we'll just give them more bass because that's what they said that it needs. And a lot of headphones out there sound good because they have added that extra bass. But I really think, and I've never seen published papers on the subject, I really think they do it because they just listened to it and said it didn't have enough bass. But no one's really delineated exactly what this transfer function needs to be and why it needs to be that way. And I think what I've done today is try and explain how I see the solution to the problem.
You mentioned Harman and comparing speakers, and it reminds me of their what they call the Multichannel Listening Lab, where they can actually put speakers behind an acoustically transparent cloth so you can't see them, and they're on pneumatic platforms that move them around, randomizing their location, and then they have people come in and evaluate them. Is there any similar sort of thing that can be done with headphones? I mean, obviously you can't put them on a pneumatic tray and move them around, but can you blind test headphones somehow?
Well, I think number one is I think you got to get Sean Olive on to talk about this in more detail. But
yes,
and he has in fact tried to create or design experiments that allow for this to happen, and that is to be able to do subjective double-blind screen tests of headphones, which you've just described is a bit of a challenge.
Yeah, because
you can. One of the papers that he published was quite interesting in that he took two headphones, or no, maybe it was the last paper he did. He took a number of headphones and put the target function of each of those headphones into. So he measured the headphones, and then he made one headphone sound like all the other headphones by making their transfer, creating an inverse curve, and then creating a transfer function that added the room gain. And he made a transfer function that was the inverse, so that you could equalize out the characteristic of the headphone you were wearing and add the equalization of the headphone under test, which means that you can have the same pair of headphones on and listen to the transfer functions or timbre of the different sounds of what a different headphone would be, and you could decide which transfer function you like. And then if you like that transfer function, that's the headphone that you like. So, and then if you put that headphone on, it should sound the same. And designing experiments that do this accurately to delineate psychology from human beings is not easy to do. But
not
Sean,
at all easy, I would think, yes.
If anyone can do it, it's Sean.
Right.
Because he's done it in many, many different areas before.
I have a somewhat different question from the chat room, but I'll ask it now since we still have a little time left. Mm-hmm. Aphex is asking about what your thoughts are on the Razer Tiamat with 5 drivers per ear cup for positional audio. I don't know if you know that particular model, but if you don't, I would generalize the question to what do you think of multiple drivers in earphone cups to simulate directional cues or provide directional cues?
Well, once the acoustic energy is at the entrance to the ear canal, having the source in different places may not serve. I think you could maybe improve. It would take an awful lot of processing to be able to map the driver that's for the surround, to have what angle it's at, that would have the transfer function for that angle, for that particular individual. I think the apparatus is what you would need, but the processing you would need with that apparatus, I don't believe exists yet. So, and I know that some people are working on it. One of the challenges of a headphone, I just want to mention, is everyone who wears headphones knows that except for a binaural recording, when you put a normal recording on, put on the headphones, all the sounds are inside the head. They're not outside the head. And the ability to take the sound outside the head is one of the challenges I think, I would like to achieve. And I think there are ways to do this. It has to do with a bit of crosstalk between the 2 ears, and also directional cues and understanding the frequency response from all different directions. Once you can characterize that, I think you have good controls. But again, that will require huge processing. I'll just add one other parameter that would be very helpful in improving the sonic experience, or the musical experience you would get with on-ear headphones with music that was recorded to be played back on loudspeakers, would be to include a head tracker, so that slight movements of the head would the sound won't move with the head. The sound will stay in the same place no matter where you move your head. And to the brain, that will be much more convincing that the acoustic event that you're hearing is real. Part of the problem with wearing headphones is that there is no head tracking. When you move your head, the sound moves with your head. And right. If the speakers are in the room, the speakers don't move when you move your head. They stay in the same place. So right, I think, right. And let me say that there's more to come on this subject.
Good. Well, we'll have you on when you can have more to say about it. I will say that
first we need to get the target function right. Right. And then secondly, we can enhance that. And one of the objectives is to get the sound from inside the head outside the head. Well, this brings up possible.
I think it is too. And it brings up a point that a number of people in the chat room are bringing up, which is, for example, the Smith Realizer, which simulates the sound of speakers outside your head and includes a head tracker, in fact, a thing that you stick on top of your headphones.
Yeah, I'm not saying it's a new idea. Many people, like I said, are working on this. And now today, there are devices. I mean, with all the accelerometers that are used in automobiles and cars for collision and tracking and direction and all those things.
There's even smartphones now.
Exactly. So there's a lot of chips devices out there that could be implemented in a headphone that would take the listening experience to even another level.
Yeah.
And I believe this will happen.
Have you heard the Smith Realizer?
No, I haven't. But I've experienced this kind of phenomena. Back in the late 70s, we listened to, it wasn't quite the same experiment, but the experience and the realization was similar in that that KEMAR that you showed on the screen a bit earlier can also be used to do recordings and binaural
recordings. Yeah, putting microphones in those ears.
Well, those ears do have microphones in them. So
yes, of course.
We just have to plug it into a recorder and put them in a in the audience, and boom, away you go. But with KEMAR, we did an experiment where we were trying to determine, what effect a room has in doing A/B comparisons. One of the things that we tried to do was, in a room or a group of where you have a group of loudspeakers, we were trying to find the perfect target function for a room. So when we were doing A/B comparisons between different loudspeakers and how they coupled into the room, and then listening to them was very difficult to do because the physical speakers were in two different locations. You had to switch from one speaker to the other. What we could do with KEMAR is we could make a recording with KEMAR of a loudspeaker with a passage of music, and then we could change the loudspeaker and play the same passage of music with a different loudspeaker with KEMAR. Then we could take those two recordings with a pair of headphones and A/B the two loudspeakers that were in exactly the same position in the room. They were just there. They were just there in different times. So with that experiment, we had a setup where KEMAR was in the listening room. There was a loudspeaker, and in this case, it was an experiment that Floyd and Sean were doing. That's when they both were at NRC. And Floyd would come in the listening room and walk beside KEMAR. And in the other room, beside the room that this listening was done in, there was a chair with a pair of etymonic, completely insert hearing devices.
They're like sort of like earbuds.
Well, they're earbuds, but they have just a long tube, and that tube goes right down to the eardrum.
Oh man!
So it's about, it can be put down as close to about 1 millimeter from the eardrum, so that now I'm not hearing any of my ear canal, and I'm not hearing any of my Pinna or anything. I'm just hearing only what KEMAR is doing, and I'm sitting in the next room. And so we started to do some experiments, and what was kind of interesting is, first of all, Floyd would come up and he'd whisper in my ear, and you could that eerie feeling when someone's whispering behind you and there's nobody there. It's very strange. And then he would walk out into the room, and as he was walking in front of me towards the front, his image of where he was became kind of vague. So we realized that, and this is well known, that your ability to image things in front of you, I guess because you have eyes, you don't need to do that very well because you can see what's there, is localization in the front is very vague because sound is coming to both ears at the same frequency response at the same time. It's very difficult to see exactly where they are.
Well, if you're directly in front of yourself, if something is directly in front of you, like right in front of your nose, but if you're off axis even a little bit, I was always under the impression that your ability to perceive directionality was better in front of you than behind you.
No, it's better behind you.
Really?
Yeah, because if it wasn't, you wouldn't survive.
I remember Tom Holman telling me once, though, I'm sorry, just one quick point here. Tom Holman telling me once that having more speakers in the surround channels around you is not as effective as having more speakers in front of you because of, he claimed that the directionality was better in front of you than behind you, but you're disputing that.
Well, me personally, I'm much more sensitive to a sound behind me than I am in front.
Huh, okay.
I'll give you an example. If you're at a movie theater and you're watching a movie, which is quite profound, it's quite loud in front of you, and somebody's sitting behind you crunching on popcorn, it drives me nuts because I can't tune that out. My anatomy will not allow me to do that because I'm so sensitive to what's going on behind me. It's part of survival.
Yeah, okay. All right, that makes good sense.
And maybe we don't localize as well, but I'm far more sensitive to sounds. If something was crinkling in front of me and I was trying to watch a movie, it wouldn't bother me at all. But if it's behind me, it drives me crazy. I don't know if other people experience that, but I do.
Yeah. Okay.
But let me just say that with this tracking to try and get the sound outside the head, I think that's something that could just simply take the listening experience to another level. And that would mean that recordings that were done on stereo speakers to be played back in rooms could be played on headphones and still sound like they're being played outside the head.
Right. Have you heard DTS Headphone X? It's another example of a high amount of processing power being used to simulate the sound of speakers outside the head.
Right. And what they do probably is have some kind of a algorithm that takes a bit of the signal from one channel, delays it so that it comes in the other channel with the head-related transfer function, EQ.
Yeah. Right.
And,
something like that.
That requires a lot of processing. And I think, well, I have some theories, and you'll hear more about it in the future.
Okay. Very good. If you haven't heard Headphone X, I'm pretty impressed with it. It doesn't have a head tracking function yet. I had Fred Kitson, the CTO of DTS, on my show a few weeks ago now. And I asked him about head tracking, and he said, "Oh, you've taken a peek at our crystal ball. This is what we're working on in the future, using in particular the facial recognition features in many smartphones and so on, which the algorithm at some future point will be able to see how you're moving and adjust the algorithms accordingly."
Oh, interesting.
So that's kind of an interesting idea. Yeah. Well, listen, Paul, I want to thank you so much for being on the show. It's been really, really fascinating, very deep and technical, which we geeks like a lot.
Well, I hope I've answered. I hope I've answered some questions, and I hope I've created some questions so that we can do this again.
Good. We shall do it again. I really appreciate you being here. In fact, I'll see you later this month at CEDIA.
Yeah, we have an appointment.
We do. I'm going to do a little video interview with you there, and that will be on avsforum.com. Meanwhile, if you want to find out more about PSB speakers or headphones or Paul Barton himself, just go to psbspeakers.com. Thanks again, Paul. Really appreciate it.
Thank you.
You can find me, of course, at avsforum.com. You can email me at scott@twit.tv. And you can follow me on Twitter at htgeekscott and also at avsforum. You can find previous episodes of Home Theater Geeks right here on twit.tv/htg or on its YouTube channel, youtube.com/twithomtheatergeeks. Next week, my guest geek is scheduled to be David Katzmeyer, the chief TV reviewer at CNET. And we're going to be talking all about how he reviews TVs, what he thinks about OLED, UHD, curved screens, and all of that jazz. So that should be a fascinating hour. I do hope you will join us then. Until then, geek out.